camera's on. I talk about the fourth uranium boom, but this slide, of course, only shows three. The first one being the World War II boom for uranium, the scramble. But I just wanted to point out that this peak in 1974, which was part of the oil embargo, was also part of me being turned from a volcanologist into a uranium geologist, because the USG has formed a whole branch of uranium storing resources, and so they hired a lot of us. So, but anyway, I'm just going to spend some time talking about why I think maybe the fact that we're going up in price a little bit here might stay, that maybe this time nuclear power might stay around. There's several reasons. But in the meantime, let's just talk about how it got started and how we got such a bad rap for uranium. But it was basically after the race for the military supremacy during World War II that it created huge environmental hazards and health risks throughout the world that left a multi-billion-dollar Cold War pollution legacy, basically, and one that people just won't let go of. It doesn't matter how good the mining companies do right now on cleaning things up. And I mean, we certainly don't leave tailings unprotected. They're not allowed to be transported by water and wind anymore. But some of the environmentalists, some of the Indian nations, specifically the Navajos, will not let go of it. I mean, we're talking like 80 years ago. So we've learned a lot of lessons from that. And this is a Key Lake mill in Canada, the last one. Whoops. It was MacArthur River, which I'm going to get back to in some of the other slides later. This is just talking about some of the various deposits around the world. And speaking of cleaning them up, this is the Latal mine in France, and this is the mine during mining, and here it is after mining, and it looks like you could go swimming in that lake. And then this is one of the breccia pipes in northern Arizona. This is a pigeon mine during production in 1989, and here's a pigeon mine afterwards. And probably the only reason you can really see it is because they planted grass, and there's no native grass around here, so the grass is doing better than the native plants. Otherwise, you couldn't even tell where the mine was. So this is some of my thoughts as to why maybe nuclear power will be around for longer this time. But the US politicians and the environmentalists are sort of realizing that this climate change deadline, for what it's worth, for carbon neutrality just simply can't be met in the US without nuclear power. An example of this is in New Jersey right now. They have two nuclear power plants that were getting ready to be decommissioned. And they realized that without that nuclear power, they cannot meet the 2030 deadline on carbon environment. So the US government agreed to keep those nuclear plants open. They gave them the money to refurbish them, and so they're going to try to keep them open. So there's one reason right there, and I think that's probably a strong reason why we might still have a good chance of having nuclear power. And of course, the Russian war in Ukraine is emphasizing the need for nuclear power. French, of all people, after being 70% nuclear power, had already started to decommission two of their nuclear power plants. And they had, one is totally decommissioned, but Michel Cunet was just telling me a couple of weeks ago that because of this, they reversed directions and they're not going to decommission the second nuclear power plant. So I think there's going to be a push again in France for nuclear power. And in 2022, the US Congress passed a bipartisan infrastructure law funding nuclear energy. There is one nuclear power plant being built in Georgia, and hopefully there's going to be more. I just wanted to show, and this is something everybody sees, but this, I was over working in Slovakia years ago, 2011, just before Fukushima. And this was just a picture I took when I was there, going to the castles, and this is in the wintertime, and they have a lot of wood burning and coal. So that's what it looks like, not that those of us don't know that. And here's in the summertime when there isn't the heat generation. So the other questions are what arises from the very large footprint occupied by solar and wind, and what could be very valuable land, a lot of it. And if you take a look at it, you can see that particularly wind takes up an enormous amount of footprint compared to nuclear. And when I was trying to look some of these things up, I realized that 95% of the sites where I was looking up, like the footprint for uranium, nuclear, they're actually environmental sites, and they have everything so twisted, and it's hard to get facts anymore on the internet. This came from the Nuclear Energy Institute, where I figured I might get some accurate information. But they try to make the uranium footprint bigger by adding in uranium mining. Well, a lot of the high-grade uranium mining is actually underground, so it doesn't have much of a footprint. But they don't bother to put lithium mining into the factor. So none of the mining is considered for these two, but it is for nuclear. So if you look up some of the data, you're going to get all different results from it. And this, I think a lot of people already know this, but this is the, and this is it's actually about that big. You can see the scale down here, barely more than a centimeter, and that's equivalent to 1 ton of coal when it comes to making energy. And they're always talking about nuclear power plants. Well, windmills aren't a panacea either. You have transmission gear failures. And on one of the things too that makes them take such a large footprint up is they have to be kept fairly far apart because they interfere, the turbulence interferes from one to the next of the windmills. And then lastly, I'm going to talk a little bit about the rare earth elements that are actually significantly enriched in uraninite. Michelle Koné first started doing some analyses on Shingopalikbi. Jim's going to have to correct me on that one. And MacArthur River, and then we did some jointly on the Dredge pipe. There's some pretty high rare earth element values. And you don't find these, as far as I can tell, in sandstone deposits, but in the higher grade deposits. And what's really remarkable, and I have analyses, I put more in the DREGS newsletter, but I just summarized these. This is your average crustal abundance to give you an idea. The heavy rare earth elements are the ones that are actually the most expensive and are in demand, and even China's Bayan Noble deposit doesn't have a lot of the heavy rare earth elements, but we have them in the uraninites, and this is actually uraninite analyses. You can see that they're many times the average crustal abundance.
So that's a probe sample of a uraninite. Is that what that is? What's that analysis of?
It's analysis of uraninite, and it's done by laser ablate ICP mass spectroscopy combined with microprobe.
Okay.
So we have to do the microprobe analyses on the uraninite to get the uranium analysis, and then that's standardized against the results for the oblate ICP. Got more than you wanted to hear, right? And this is just a quick graph showing and Michelle likes to do things with normalized chondrite. I put them up so you could get just a basic idea. And I know reading data tables isn't great, but you could get a basic idea compared to average crustal abundance. But still, this is normalized chondrite, and you can see it's thousands of times. This is MacArthur River in Canada. This is Shea Creek, Canada. This is Shinkolobikwi. And then this is a couple of the Dredge pipes in Arizona. So even if nuclear power, though, is now accepted, the biggest impediment that we have to expand the industry is a shortage of geologists, engineers, nuclear scientists. And France particularly is noticing this because they're trying to expand now. We just don't have people trained. And that's why I thought, well, maybe it'd be a good idea just to give some of the uranium basics, hoping that people under 40 would show up. But just because I don't think there's been too much taught about uranium in the last 2 decades. Yes.
Along that vein, Karen, does the USGS have a true uranium geologist?
I doubt it.
Finch died, what, 10 years ago? He was it.
Yeah.
I remember I was consulting a couple of years ago, and the DOE didn't even have a uranium.
No, they don't. It's fairly sad.
It's a cluster.
So if we decide we're going to increase our nuclear power plants, we certainly have to increase the education level. But let's go into some of the basics now real quick. And uranium is classified as a lithophile element, and it's abundant in granitic rocks. It's about double, the granitic rocks are about double the average crustal abundance, which is simply about 2 parts per million. And the valence states are reported to be from 2 to 6, but the only ones we need to worry about in nature really is +4 and +6. Uranium geochemistry is really pretty simple compared to a lot of the other metals. If for an element that's relatively rare, 2.5 parts per million, it has an exceptionally large proportion of all the known minerals, like 5% of the known mineral species. As of 1984, and I realize this is a long time ago and there's lots of new minerals, but there aren't that many new uranium minerals. 160 species contain uranium as an essential element, and in many additional species, uranium is known to play a significant substitutional role. And it's very happy to substitute for calcium, anything that's the same as +2 charge, +4 charge, and that has a ionic radius similar to the uranium. But of course, they get a lot of attention because they have a beautiful array of colors exhibited by most uranium minerals. So it brings them to everybody's attention. And I'm going to wake you guys up with some uranium pictures. So here's one here. This is a copper uranium phosphate. It's torbanite. And if you've ever wondered what the difference is between, you see in these uranium minerals is meta this and meta that. Well, if you look at the meta torbanite, you can see that it has 8 waters in it. If we go back and, sorry. If we go back and look at the torbanite, look how much clearer it is. It's not opaque. And here it's got 8 to 12 waters. So what happens when it becomes a meta mineral? It's because it's lost some of its water. It also loses some of its pretty translucency. And here's carnotite, which anybody in Colorado is very familiar with, I'm sure, because we find it all over the Colorado Plateau. And it's a potassium uranium vanadate. This happens to be from the Anderson mine in the Date Creek Basin in Arizona. They're lovely crystals. Unfortunately, most times carnotite's kind of a yellow blobby mineral. It doesn't form good crystals. They're very, very, like it forms crystals, but they're very fine grained. And here's a metatheoyamanite, malachite. So as I mentioned a little while ago, uranium has 2 primary valence states in nature. It has a +4 and a +6. +4 is totally insoluble, and +6 is soluble. So when you're drinking water and you're worrying about uranium in your water, it's +6. And it, like I said, it's very soluble. In fact, the South Platte River at Julesburg actually has 60 parts per billion uranium in it, and the average safe drinking level is 30 parts per billion, but it's all natural. And uranium, for the most part, kind of goes in your body and goes back out again, unless you're a smoker. All bets are off then. And here's some uraninite, and this is from the Congo, and Jim's going to talk about this deposit, I think, at least mention it a little bit. And for uraninite samples, I brought one along you might want to see. There's lots of them in the back table there, but this one's actually a beautiful crystal. It's actually shiny, very, very shiny. I put it up here because I didn't want to get hit with some of those rocks back there. So most natural uraninites are partially oxidized with compositions between UO2, which is a composition of uraninite, and UO 2.67. Pure uraninite is brick red, but it quickly oxidizes to UO 2.04, which is brown. At about UO 2.07, uraninite becomes black. The fact that it oxidizes so fast is one of the reasons that it received back in the 1940s and 50s, it received lots of different names. They've got a name called pitchblende, which I'll get on my soapbox about that. And there was gumite and all different materials, but uraninite oxidizes. And some of the work I did in the Hopi Buttes diatremes, when I tried to work on it with a microprobe, I couldn't even find what looked like uraninite. I could get uranium, but I couldn't find anything that stoichiometrically would make a mineral. So it's so oxidized, it's got so many other elements mixed in with it, it's just kind of a gunk. And so they called it things like gumite, which aren't real minerals. And here's what happens was, this is some uraninite. This is from the El Dorado mine in Northwest Territories, and you can see it's sort of botryoidal, actually quite hot, but you can see some hematite up here. So this has been oxidized a bit. And when you get this botryoidal uranium, the French like to call that now pitchblende, but there is no crystallographic difference between uraninite and pitchblende. Pitchblende is not a mineral species. It's not recognized by the International Mineralogical Commission. And you won't find it in the Fleischer's Gallery for those of you who like mineralogy and like to look up things. It has to be in that glossary to be an official mineral. So I just generally call it all uraninite. So there's basically no physical crystallographic difference between the pitchblende and uraninite. And the different patterns in the powder diffraction file for pitchblende and uranium, the name pitchblende was assigned to specimens where old patterns were taken without calibration, and the cell constants that were quoted in Frondel are probably bad. And this is a uraninite sample from the Czech Republic, and you can see some of the oxidation on the edge. This is some yellow, either carnotite or T-yamanite, one of the yellow uranium minerals. And here's some more. This is from Bohemia, it's another specimen of uraninite. Now, the roll front. All of you have heard of roll fronts. So basically what a roll front is something that was identified in Wyoming. In Colorado, more of our deposits are tabular, and same thing with New Mexico. But the roll front makes kind of a nice little cartoon here. You've got the oxidizing groundwaters coming through, and when they hit regionally reduced rocks, they bring minerals out of solution. Here you've got a hematite core, and then you get this siderite sulfur, and then uraninite next. And then we get some molybdenite and pyrite, jordicite. And then in the reduced area, of course, there's more pyrite. And this is not just a cartoon. Here in the Turkey Creek, we actually have a little roll front, and it's right along 285. It makes for a great field trip if you haven't been there. But the fluids came along just like in the last photograph. Now, the fluids are coming from left to right. They're doing the same thing here. They're coming from left to right. And what's interesting is here's your uraninite, but up here, see how that's a little bit bluish? And remember on the outer edge, it was showing molybdenite here. And this was a mineral, gilseminite, right here is a blue molybdenum mineral, and it's on the outside, just like in the cartoon. And there's a little bit more of the blue down here.
Current scale on that? Ballpark?
Up like that.
Thanks.
Jim,
Yeah, you're looking at probably about 6 feet high there.
okay, you can see. And Jim's been out of shape because what I did was a stupid Turkey Creek roll front. It goes the wrong way. So here's the actual roll front. I flipped the slide upside down. So it was so it was going the same direction as a roll front, so you could see it easier. But here's a real field shot going the wrong way. So, and there's the blue ilseminite down there. Yeah, it's a neat field trip, neat place to go.
Those sands are oil saturated as well. The sands were oil saturated where that roll front occurs.
Oh, they're saturated with oil?
Well, yeah, here's your reduced environment.
Yeah, well, I know it's reduced, the rocks are reduced. Is it actually dripping there?
Yeah.
I don't remember that, but it's been 20 years since I took that picture. And then actually DREGS had a field trip back in about 2005 to the Uranium mineral belt. And this is the SM18 mine. And there's Jim in his younger days. There's Jim Piper, who does our newsletter. There's Paul Martos there. And anybody else see themselves in this picture? And again, that's a mine that has organic material and it's reduced to uranium, and so the uranium's in the organic material. And a lot of places where we had petrified wood, and this is actually not the Chinle Formation, Arizona with petrified wood. This is in Patagonia, Argentina, and the formations down there look like they are the Chinle Formation. It's the greatest example of continental drift I've ever seen. And so this is petrified wood. It had some organic materials in the core, and here's carnotite. This yellow material is quite radioactive. And this is some coffinite. Unfortunately, some of my slides are getting cut at the top here, so you're not getting to see the formulas. But coffinite, one of the only other significant uranium minerals that's reducing. Almost all the rest of them are in the oxidation state. And one of the things that I caution you for is a lot of times they've identified material as coffinite, but if you take it to the microprobe, there's no silica, and coffinite has silica in it. So it's more likely that most of those are, an awful lot of the ones that I've found are actually uraninite. And here's what you find on the Colorado Plateau. You find a lot of the carnotite. And pay attention to the formula because it's going to come back. I'm going to show you another mineral that is a new mineral, relatively speaking, it's 40 years old, but a new mineral that has a substitution for carnotite in other deposits. And here's the T-yamanite. Again, it's very similar to carnotite. It's the same formula, except you have calcium in the structure instead of potassium. So I was going to look at the Pina Blanca uranium district. I'm going to look at some of the different deposits right now. This was one that was in Mexico, and this is they have several deposits here. This is the Nopal 1 deposit, they call it. And it's got a whole series of really neat uranium minerals here because it's got the oxidation and then it's got uranium minerals. And this is one of the ones that's there, it's sodite. And here's some weaksite. And the main deposit that they had that they were mining, the Mexicans were mining, was the Pina Blanca Margaritas deposit. And when we took samples back, I took a bunch back. I had a minority student that was going to train how to use the X-ray diffractometer, and he brought the sample back and said, it doesn't match the pattern for carnotite. And I, well, let me show you. But he was absolutely right. The 001 plane wasn't there, which you would normally get for carnotite. So what has happened is the cesium has substituted for potassium. To be a new mineral, it has to be more than 50% of the potassium has to be replaced by the cesium. And there were only 4 cesium known minerals at the time. So it was kind of neat to see this new mineral. Again, it's just very, very fine grained yellow material. And this is, we just, doing the new mineral structure, we had a real detailed analysis. We had to pick the gradings out, but you can see it has 17% cesium and only 1.2% potassium, and then the rest of the mineralogy is the same as carnotite.
Aaron, how did you come up with that name?
Oh, you know, Pete Madresky and I were working on the new mineral, and we were sitting around drinking margaritas, and Pete says, you know, it's too bad we can't name this margarita-ite, I guess he called it. And because you have to name it after a person or after the deposit. And I said, actually, we can, because it came from the Margaritas deposit. So it's really pretty straightforward and simple. So it's still my favorite drink. We did some synthesis experiments just to see how what made the cesium behave. And it turns out that it really needs to go at temperatures around 200 degrees Celsius to have the cesium substitute for potassium. But it does not appear to do this in any significant degree at lower temperatures. And when I collected the samples, it was kind of from a trench, in the trench area. And the carnotite was all over the place. It was huge, geographically, it was pretty large. And after we look back at it and you look at that deposit I showed you a little while ago, the Nopal 1 deposit, and this is only a couple of miles from the Margaritas deposit. You can see it almost looks like a hot spring area. And I think that's exactly what happened at the Margaritas deposit, is that it was a hot spring, because one of the other guys, his name's Peter McGaw, some of you know him, he went down there to sell margaritas. He was going to make a killing out of this. So he goes down, he collects a whole pile of it, and he brought back and gave me some of it. And because he kind of asked me where I got it from, and I tried to describe it, but without being there, it's hard to tell. And so he sold a bunch of it to the British Museum. And the next thing with USGS get a call from British Museum that our Margarita site is just a big fraud. Well, the sample was at the original samples at the American Museum, like it's supposed to be. And so we had to write letters back and say, you need to take a look at that specimen, because that really indeed is, and we sent them all the data, and we never heard anything more about it. So I wasn't happy with Pete McCall. He made a lot of problems for us there, was trying to sell the mineral. So I think it was just very restricted right around that hot spring area. And here's another uranium mineral to keep you awake. This is autunite. Name's actually up there under this screen. But you can see the formula. It's a calcium uranium phosphate. Here's a mineral ulricite, a calcium copper uranium phosphate. boltwoodite, potassium uranium silicate, hydrogen in it. And here's dumortierite on torbanite. This is the, dumantite on top of the torbanite. And you remember, you can tell that's not metatorbanite because it's nice and translucent. And here is, trying to get the name out because that buried sire. Anyway, it's calcium uranium arsenic. Germany. This is masonite. That's from Mossani Shaba Zaire. And another uranium mineral. Flipping around to see if it's going to give us the top of the screen at all. This is metazonerite. This is actually from the Grandview mine, the Grand Canyon. This is a breccia pipe. Uranocercite. Oh, and then there's the what they call Vaseline glass or uranium glass. I'm sure you've all heard of it. I brought a piece here for everybody to look at, but this is hexavalent uranium, not the covalent. And when you get hexavalent uranium, you can get some chalcedony that's real fluorescent. It causes a lot of fluorescence in minerals, but there you go.
Holy mackerel.
This one has little cherubs on it. It's an old piece from around 1900 when they were making it. It's from the Czech Republic. By the way, I have a really nice little portable UV light and I misplaced it. So my girlfriend loaned me her scorpion light. It works better than my fancy, expensive UV light does. It came from King Soopers. And this is the McLean Lake pit in Canada. And here's a MacArthur River mine. So I'm going to talk a little bit about MacArthur River. One of the things I haven't emphasized is that most of the deposits in the Colorado Plateau, we're lucky if they're 0.1% U3O8. When you get up to MacArthur River and the Athabasca Basin, the MacArthur River's average grade is 20%. And Cigar Lake's even higher than that. And some of the other mines they're all very similar, 10%. And we always thought they'd take over the world. But one of the problems that's happened is that in Kazakhstan, the Russians have subsidized their uranium deposits. They're low grade, they're 0.03, they wouldn't be economic by anybody's standards, but your Russians have subsidized it and we're buying it from them. MacArthur River mine actually ended up shutting down a couple of years ago. And they have it on standby. I think it's going to open up now. The price of uranium is up over $50, but I've heard from a lot of mines that it takes about $60 to keep most of them going. But again, the average plateau deposits are only about 0.1%, and the drift pipes in Arizona are 1%. They're the highest grade material we have in the United States. Got rare earth elements in it. However, Obama withdrew the land, and it's still withdrawn. Energy Fuels Nuclear, who owns the mill, the White Mesa Mill in Blanding, Utah, has actually really intelligent. I can't believe how smart they finally put rare earth elements in the mill circuit. So they are processing now and trying to pull rare earth elements out of the samples. They're bringing in sands from the East Coast to monazite sands to pull some of the rare earth elements out. But it's, the only real operating mill we have in this country. The rest of it's all leaching, acid leach. But here's the MacArthur River mine, and it's mined almost totally robotically. I mean, it's not like it can't go underground. I was underground with a whole group of people from the IAEA that I brought in, but it's long-term exposure that would get you. So they've been doing it robotically, but they have to. Here's a catch. If you remember the picture of the McLean Lake deposit that I just showed you, there's water everywhere. So it's a problem. They have to freeze the walls of the mine, and they almost lost the entire mine a couple of years ago when a drill operator broke through the wall and started flooding the mine. This was in 2004, and they barely saved it. In fact, they wouldn't have if they hadn't. So they shipped the pumps from the potash mines in southern Canada up to keep up with their pumps couldn't keep up with the water flooding in. So it's tough mining, it's expensive, very expensive mining. When the cost is lower, the breccia pipes in Arizona are actually more economic, despite the fact that they're only a 20th the grade, just because the mining costs aren't so high. And then they're doing it, you can see these are big cores, they're 6 feet in diameter. And they just drill down and pull these cores up. And here's the MacArthur River ore. It's a polymetallic rich matrix. And here's a breccia pipe in northern Arizona. So again, the top of the slide's cut off. And then just to show you the breccia pipes, the ore is down about 1,000 feet. And here's one of the breccia pipes, and this is the red wall limestone. There's all types of deposits. Uranium really makes a lot of interesting deposits. It's an exciting field to be in. But you can just see some more of the breccia pipes, and they have inward dipping beds. But again, they're really the pipe itself is really only about 300 feet in diameter. It doesn't do that much destruction when they mine. I just thought I'd throw this in if you want to see a pipe, but this tells it all. The breccia pipes are not volcanic. There's no volcanic rocks associated with them, and time and space. There's solution collapse, just like this pipe in Guatemala City. And I'm betting that's not too much bigger than the average breccia pipes. And this is kind of an interesting slide. You know, I'm showing you the oxidation reduction, how you oxidize uraninite. Here's an oxidation reduction front, right here. This is a sandstone, there's quartz grains, there's your matrix, and here's the oxidation front. There's uraninite substituting for the calcite matrix, and pyrite substituting for the quartz grains. It's quite actually dolomite cement, not calcite. And this is just a quick slide showing this is the original uraninite. This is some secondary materials, kind of botryoidal. It's probably more oxidized, it's late stage. And I just wanted to overwhelm you with a chart that I carry in my purse all the time, but because I can't remember it. But again, for those of you who have questions, and most of you probably know the answer to this, about U-238, 235, and the bombs, basically U-235 only makes up 0.7% of the total uranium. Most of it's U-238, U-234 is even less. And so that's always been the problem, keeping the countries from the bomb, is they've got to use a centrifuge, they got to get it purified up over 99% or 98% to have a bomb. Nuclear reactors only require about a 15% enrichment, something like that, which is not that hard to do. So there you have the decay series. And this is, again, slightly out of date, but it doesn't make that much difference since there hasn't that much of a change in nuclear power in the last years. But here's the world production. Here's the world requirements, world production, and our requirements exceed the production. But again, there's stockpiled uranium. And just this, I just threw this up to just show you how the US was a big uranium producer, and now we're just about nothing. And this is a slide showing you the consumption for nuclear power. Again, I apologize, at the top of the slides under that material. Anyway, this is North America actually has 31% of the nuclear power in the world. And I throw this in again, just showing you where some of the resources are. These are the recently assured resources. This is Australia, and they have a bunch. And the Olympic Dam was one of the biggest deposits. Since I'm talking about everything in the Americas, I thought I'd just throw up one for Australia. But here's Olympic Dam, and one of the things is a big copper deposit. But the uranium was just supposed to swamp the world with uranium. One of the problems was that uranium, the copper ore has uranium in it, and it really hurt their production. I think by now they've figured it out. And then this is just to show you on the Salton Sea, uranium's everywhere. The Salton Sea has 1 part per million uranium, but it carried in solution. But the scale on the liners has 1 weight % uranium, and it's formed within 90 days. Almost done. Oh, there we go. Thank you, Lauren.
What do they do with that? So you can't just have 1% uranium lying in a yard like that. That's
Well, they scrape it out. I don't know what they do with it. They pull, you can see, let me go back. They pulled the pipes they've got the pipes pulled out, so they can't really use those anymore. And you gotta send it off to a uranium graveyard somewhere. I mean, you could send it to a mill.
You'd think you could, right? You'd think blanding would take that
Yeah,
stuff,
exactly.
right?
1% uranium is better than the Colorado Plateau. And I just bring it up again, you know, whether nuclear power stays around or not, I don't know, but it's got a lot going for it now. And I think whether we like the global climate change, it is a plus apparently for nuclear power. And you can see the price did drop after the Fukushima accident, but not like it had back here in 2001, it had hit a low of $6. So other than the subsidized uranium from the Russians and Kazakhstan, nobody's going to mine at that kind of price. But here we've hit, today it was $50.80 or something like that. So it's up there. It's been kind of looking around in the last couple of years, see what happens to it. But we still have to, you know, one of the things that we mentioned in the chart is that, you know, we've got, so there were so many people that wanted to have disarmament, no uranium, get rid of it all. But is Russia going to do that? North Korea, China? That's never going to happen. It just isn't going to happen. And people are going to have to be practical that uranium's everywhere. The rogue countries have it. It's not hard to find. It's not like it's that rare. And so having a nuclear power plant, it isn't going to give them any more access to uranium and to build a bomb than what they can get in the earth. Yes.
Major problem with uranium power plants in this country is political.
Well, I know.
Quite simply, every time somebody brings up uranium, the press goes out and mentions 3 Mile Island and Chernobyl.
But you know, now.
Neither of which were actually a problem that you would have gotten in this country.
Right, exactly.
In TMI, the amount of radiation that went up the stack was barely above background.
Yeah, I know.
And you're exposed to more radiation from cosmic rays every time you fly in a plane at 30.
You know, those same people that object to nuclear power are all up in arms about climate change. And they gotta have climate change, or they aren't gonna get it with just solar and wind. And as we all know, and most of them won't admit, if you tried to plug Tesla, everybody had Tesla and plugged it in, our grid system would be non-existent. And that's gonna pull the grid system down. So somebody's gonna have to face up with some facts here soon.
On a conservative basis, if you were to produce all the US's power with wind, it would occupy a land area equivalent to Pennsylvania plus New York, plus Connecticut,
I think it's
plus
more
Rhode
than,
Island, plus Massachusetts,
I saw this
Vermont,
map,
New Hampshire, and Maine.
and I couldn't find it when I went.
I've calculated this.
Yeah,
There's a bigger problem.
And this is a bit conservative.
yeah,
There's a bigger problem with wind though. That is, you only got wind when it's windy.
that's right.
And uranium, you have to replace the baseline power systems, which is currently from fossil fuels. You won't replace it 100%.
I wanted to make
with
one-
solar or wind unless you get a lot more storage.
On the lines of deposit for nuclear power. As you probably know, nuclear power, like you're saying, is 24/7. And they got to do something with it during the odd times. And the Palo Verde nuclear power plant outside of Phoenix, which by the way uses wastewater for their coolant, they have done that for decades. Now they have to fight the golf courses for wastewater. But anyway, what they found that's useful to do with their excess power at night is the Salt River has 4 reservoirs on it. The Roosevelt, Canyon, Saguaro, Paschis. And I noticed last summer when we went to take our boat there that they were all full, you know, in contrast to Lake Mead and Lake Powell. And I thought, well, that's really weird. And then I learned, I should have known this, but I didn't. At night, they take the power from Palo Verde and they pump it over to these reservoirs and they back pump all the water, like they're creating batteries with these reservoirs. Then during the day, when there's a demand for air conditioning, they let the water back out. And then at night, they pump it back up. And it's like, what a genius thing to do. So my solution to the Colorado River problem is that we build a nuclear power plant in Las Vegas and we back pump Lake Mead, the water back up to Lake Mead and Lake Powell. But there's so much of the water from Lake Mead is going over the dam for power for LA. And so anyway, that's my
You're
solution.
talking about pump storage, which has been around since the 1950s.
But I didn't realize they were doing it to that level. That's a big level in Phoenix. It's really a neat thing to do.
There's a lot of pump storage plants, not in this part of the country, but out east.
One in Georgetown.
Georgetown.
Vanilla Pass.
There's one there,
Well,
but
the
not
one
the size of,
Yeah.
it's not the size of,
Vanilla Pass.
PBA or
Okay.
the Raccoon Mountain, for example.
Anyway, here you have it, and here's what we're up against, you know, there's one of our breccia pipes in Arizona, there's Havasu Falls, so, you know, although the mining is not in, you know, in areas where you have the falls, and so it can be avoided, and I've showed you how to clean the art, and I've cut into Jim's time here by about 7 or 8 minutes. Okay, Jim?
A quick question on the breakfast pipe. You had that 1,000 feet, was it stratigraphically controlled or was that some sort of temperature gradient? Why was the uraninite dumping out about halfway through it?
It's stratigraphically controlled, it's in, but I'm not sure it's as much stratigraphically controlled as it is where you have the oxidation and reduction. And I can get, this is another whole talk getting into
Yeah.
how how you precipitate out the uraninite, because we don't have organic material there, but we have H2S gas. And so it's whatever horizon the H2S was at, but pretty much it's in this upper Supai formation, the Hermit and the Coconino. And that's where it is, so. Larry?
Yeah, from the back of the room, looking forward, I see the heads of a lot of men who I think were probably uranium geologists at one time. Maybe it's an age judgment, but not you, but I was talking to Jim, to Chuck Spirakis, and he said an observation of in exploration in the USGS that wasn't really widely accepted was that the clay fraction was the only stream sediment fraction that had uranium in it, even within a uranium deposit or around them. And I wonder if this is true, and if so, it's a very significant.
Real quick, Larry, on that, because I did a lot of my early project with the USGS, which was a boring one, was doing sediment sampling. And yes, the uraninite, the highest grade when we did the NURI program was in the very fine clay stuff, but it's not associated with the clay. Because I did a lot of analyses and there's no correlation between uranium and aluminum. And if you're gonna have it in the clays, it's gonna be associated with aluminum. I think what it is a very fine fraction, once again, has the organic material in it. So there you go.
High significance for future exploration, that's all.
Yeah, so no, that's true. That's a true observation. It was always in the fine fraction and probably because of the organic material. And I'm gonna let Jim go because you guys can ask me more questions. I'm not going anywhere.
I can back up about that. If you look at these deltaic deposits, like in Elliott Lake and the Whitwaters Rand, the high grade was in the fines in the quartz grains. The larger grained stuff was low grade, even though it was the same type of pebble conglomerate.
Yeah, probably interbedded organics material. Jim, come on, get up here. You were supposed to help me out with pronunciations and stuff and some of that I've been getting. And of course, I sorry about not having the identity of some of those minerals. All right, it's all yours.
Next one.
Yeah. Oh, I guess we have to get rid of mine, don't we? I think that's what we do. Yeah, yes, we have it. Yeah, that was that. I don't put your stuff on there. The problem is it pops up. Oh, really? Oh, great.
Okay, wait, it goes. To go forward.
Yeah, but don't right click to go back to because it brings up that.
Yeah, okay.
menu, so you have to-
Well, greetings and thanks for coming along to hear a little bit of history. And this is, let me start from the beginning. First, there was a supernova. In that supernova, you can see maybe in the browner tones there, that's where iron is. But heavier elements such as the PGEs and uranium are formed there. Now, there's something in between, and it's the Schwarzwälder mine, because between it's also a Superfund site. Okay, so I'm going to talk to you about the geology with respect to discovery, mine development, and how the ore was produced. The Schwarzwälder is located about maybe, just up the road about maybe 8 miles up Highway 93. But it's outside of the Colorado mineral belt, which is outlined here in these white dots. And I just might say that that extends from Boulder down southwest almost to Durango. And here are just some of the deposits that are important there. The gold telluride district is up in here, runs approximately north-south, and then there's a tungsten district, which runs about approximately east-west. And then across that mineral belt is the Caribou Mine, famous for great silver production. But the real thing that kicked things off for mining in Colorado was John Gregory, who went up Clear Creek, finding more and more angular and placer gold, and finally the source at the mine, and it was in quartz. And I understand that he wanted to go back to I think it was Georgia, and he actually fought in a civil war. He ended up in jail, captured by the Union Army. Too bad. He took his $20,000 back. Well, across from that is the Henderson mine, or molybdenum. But on top of that, first was the Urad mine. Now you're familiar with the Climax mine, the third molybdenum deposit. Those 3 deposits value exceeded this 49,000 ounces of gold produced in Colorado. Now here's a shot from satellite of a couple of decades ago. Golden down here, and the Schwarzwälder mine in this little light streak down here below the W. But the concern was at the Rocky Flats plant, when I worked there, what about faulting that might be reactivated and imperil the plutonium works there? So a seismic line was put in here. And here are the results. The front range uplift during the laramide put great compression on this light blue pure shale. But what was resolved was it was all reverse faults. However, they did not pierce the younger Cretaceous. So it was deemed that the plant was safe with regard to the faulting. And if you want to know where the Schwarzwälder is, go from the campus, take a look, and it's here, kind of down inside the Ralston Creek Valley, and there's a Schwarzwälder located over here. Now, I pointed out 2 formations here, F1 and F2. That's the Fountain Formation. Now, the smaller formation is, you can see that easily if you're riding up Ralston Creek. But look at that F2. That's the Fountain Formation and Arcos. Okay, it's been really uplifted relatively, okay? Why? Well, there's a fault going through there, and we'll see that a little better later. So let me talk about the surface geology. This is from USGS Professional Paper 520. In white dots, I lined out section 25, and the Schwarzwälder is located here in the southern half of the section. But the main geology here is to the south, mica schist, and to the north, the green is the hornblende gneiss. Now the structures here, well, let me point out the nonconformity first. Here, there's kind of like light purple. That's the Fountain Formation. And here's that fault that really made that offset in that first view I showed you from the campus. It's the East Rogers Fault. The other branch of it is the West Rogers Fault. That structure goes at least in the northwest across Colorado for about 22 miles. And there are various ore deposits along the way. Most of the times it's written that the those breccia reefs or faults are not mineralized. But something changed. Right, Tom? Now, what I can't show you here is the geology right there because of the scale of mapping. So let's look at this section down a mile. Okay, the green was the hornblende ice. It's on this side of this zone right in here, and that's the stratigraphy I could not show. Well, on this side in front is the mica schist. But these rocks are so folded to make a synform that is down to the southwest of the section. Okay, the two branches of the fault, West Rogers Fault and the East Rogers Fault. The lithology between the two, though, is cut again by a sigmoid fault of the Illinois. And the Illinois, which is this red streak down in here, is mineralized where the section of favorable rocks doubles. So horsetails spring off from that, the Illinois vein. Well, let's take a look at that. The stratigraphy is first the mica schist, which is probably a marine shale. And then a garnet biotite gneiss, a quartz biotite schist, and a quartzite. And on top of that, there's this hornblende gneiss. By looking at the signature of rare earth elements in the hornblende gneiss, it was a basalt. Okay. So that's what the amphibole grade metamorphism did to these rocks. But for the key in the mine was that these three units, post-ictal ore, are very brittle. And that's really an important concept with respect to the difference of the two ductile units of the schist and the gneiss when we go to do the production. Okay, now we're going to look at the Illinois after this. Now, here's Fred Schwarzwälder and his dedicated wife, Martha. So in 1979, he says, I've had it with Iowa. He moves out to Golden. He takes on a job as the janitor for the high school. And he loves just walking out in the hills, picking up rocks and bringing them back. Well, he brought one like this back, this one with a lot of malachite on it. Probably didn't know what that was. However, at this time, surprisingly, two of his nephews come from Germany and enroll here at Colorado School of Mines as geology majors. He's got a couple of sons, and they also helped him out, because what he did was he took these samples and the uranium content was pretty good. Well, I don't know how he did it, but he got enough help. He actually filled a 53-ton amount of ore and got it trained up to the buying station for AEC in Salt Lake City, Utah. Two checks come back. Two $6,000 checks come back to him. And I guess that was, you know, for a lower class family, that was just great. Well, he's so interested in mining that a company then called Denver Gold, Oil, and Uranium said, Fred, we want to buy the mine. Well, how much? Here's the offer. $500,000 as a finder's fee and a royalty of 10%. I'm going to leave it up to you. Which one would you pick? Because the White families now found out that, hey, this isn't his land. His stakes were invalid because we acquired this property from Union Pacific Railroad, which came under the land grant when they put the Transcontinental Railroad in. So out of their kindness, the White family says, look, we're cattle ranchers. We would have never just found this rock or had any interpretation of what it might even be. So they said, you know, Fred, you take first choice. Okay, so it's royalty and it's finder's fee. Now, so Fred works at it, But Denver Golden Gold and Uranium, they said they work at it for a while. Finally, they're bought out by Carter Corporation. I had that rock for so many years in my truck, I decided to cut it in half and have a look at it. Well, here's those original copper minerals, kind of a purplish bornite here, and later yellow chalcopyrite with some secondary blue cobalt. And it's radioactive. Well, time goes on, and I'm working as a geologist in the Cache mine up in Gold Hill. And we're sending in samples to assay about every week. So I asked, can I slip in one of these from the Schwarzwälder mine? Well, a week later, no gold, Jim, but 21 ounces per ton of silver. Pretty cool. So Connor keeps it up, and if you might recall from Karen's graph here on the price of uranium in that was early 70s, about $8, okay, for U308. Well, Connor realized that they needed to go deeper, so they needed probably a third winds per shaft, as they call them. So the mine gets put up for sale. Anaconda says, well, let's have a look. They go through the workings. They look at the core. They look at the assays. At this time, Carter's about on the 8th level. They only see core assays on the 9th level. $8 million. Well, wait a minute. The biggest utility company powered by nuclear is in Chicago under Commonwealth Edison. $28 million. Okay. And you could stay on as the operator, the Carter. So let's see some of the highlights there. Okay, at number 1, which is even off the upper left corner screen there, that's the location of Schwarzwälder's discovery. At number 2 is the adit, which goes in called the Steve level. And that's the first level going in. So all traffic has to go through that portal. The East Rogers Fault is here at 18, and it doesn't stand out much. As you go into the portal, you're starting to work deeper, we have to get air into the mine because I'm sure that Tom can verify this with regard to radon gas. If you get caught smoking, you're out the next day. You get caught smoking the second time, you've had your job lost. So downcast air by 75 horsepower fan, the 3 here, goes in, flushed across the stopes and outer workings, and then out of vent raise or vent shaft out here at number 4. The last thing I want to point out to here is where is this main Illinois vein? Well, it goes across this area here under Ralston Creek and then joins into the East Rogers Breccia Reef. So let's look at that feature. On surface, you can see fractures at that little marker, a 75-degree dip, and we're looking north here. But look at the heavy biognetic alteration. So it must have had a lot of sulfides with it. Now let's go underground. Here on the 2nd level, it's a breccia. You see fragments in here. And then going down even to the 9th level, it's just a shear, about 3 feet wide is a shear. And going down to the 11th level, big enough for you to walk into. Okay, look at those sparklings down at the bottom of that. That's water trickling down into the mine. And to get the water out of the way, they got to pump 600 gallons per minute of. Okay, for access underground, walk into the, go through a heavy air door. This hydraulically operated or pneumatically operated, and down this down the shaft here. So I got asked to help us out with the radon at the mine. And do that by picking a place where we could put a borehole down that could really vent out that radon, which we're going to expect as we go deeper. So there was a complication though. I'm not supposed to put it where there's ever going to be any uranium mining because you're going to use it as a secondary escape. Okay, sounds logical, drill a hole, but don't hit anything. Okay, so we're gonna set up here about 7,300 feet elevation, go down to about 1,400 feet. And then we're gonna go through that and then bring the cuttings out and take them back up the shaft and then dispose of them up creek. This is a pretty cool device. It's got drill collars. They're 4 feet long and they weigh 900 pounds. And it's driving a 10-foot diameter pilot bore down. So it goes down about 1,500 feet. Then they attach an 8-foot diameter hemispherical bore head. This, I don't know, it must have about maybe 36 cutting heads on it, all scattered around. And that was a tight fit going down there. So this 8-foot diameter hemisphere is actually cut into about a third and 2/3 pieces, so it pulls it back together. Well, here's the results. Up where it says R on the screen there in green, that's where the head, that's where the heading was going down of that drill hole. And it stops right here. And here's the 7th level. I don't see any red stuff there like veins, so I was okay. So those cuttings are pulled out up to 7th level. And the guys are really working fast to get those cuttings out to the top. Well, they didn't, I don't know, somebody didn't tell me that at management. They said, yeah, that was such a great job. Let's go to the bottom of the mine. Okay, all right. So everything's brought down here. Pilot bore goes down. They put on the bore hole head for 8-foot diameter, and they get up about halfway. There's no more cuttings dropping. Somehow it bridged. Somehow. Okay, so next thing they do is, okay, we got water underground, so let's pour some water down there to wash the cuttings out. And they don't come out right away. So it builds up about a 400-foot head of water. Okay, so we got to go back and look at is it coming out yet? Well, our surveyor, Mike Gallagher, he's down here, and all of a sudden, he hears the noise, it's the roar and the rush of water. And as fast as he can run, he goes out here and jumps on the ladder, water halfway up to his shins. But he's okay. Well, let's take a look at the mining now. What's exploration? There's 2 long-ear wireline rigs working, and there's a DIMAC. The DIMAC is a really fantastic rig in that it's almost, it's all hydraulically controlled, but it only can drill 10 feet at a time. So we go in 10 feet, you got to pull it back out. Put another string of rods on, go in 20 feet, you just got to come back out all the time. Well, Bill was so astute with that rig. There's something him and all the 2 other drillers build up. If you exceed the average footage per day, and if you cut the Schwarzwälder host rocks, which are very relatively hard to drill compared to the other rocks, you get a bonus. Bill turns out to be the highest paid employee at the mine, even exceeding the manager. Okay. Now here's the mining. Okay, this is on the 9th level. The vein here is black and it goes off to the lower left, and it's marked out in red by the geologist, which are scanning with the Sheila Geiger cutter to see where the vein is. Now, if you look over the top of Ray's hard hat, you can see a grain like this, and you can see also a gneissic texture like this. This is just ideal. The vein fault is coming perpendicular to the gneissic texture. Great for braking and not for slippage. So these guys will blast. and they'll stand on higher rock. And there's also, of course, you've got to make some money here, so they bring out a slusher. This was a look at all the mine veins on this level, pulled out where the ore passes. And that brown slusher in there is 6 feet long, so it gives you an idea how big this operation was in this vicinity. Okay, after the 8th level, which was on track, down below that, the 9th level was by diesel, and everything below that was under using diesel. And here's Larry running a 1 yard loader. Here's what the ore looks like, for example. Okay, breccias. They're hematized. The sample's up here if you want to take a look at it later. And the black is uraninite. Here, around here. And sometimes it's lost, or in other words, it's been abraded off by other faulting. And here's like a micro breccia down in here. So in this sample, we're looking at 2 stages of mineralization. With the hand lens alone, in very unusual spot, I was able to see 7 periods of brecciation. Now, if a fracture is straight and it moves, there's no open space. But if it undulates and you create open space, right? Well, now, the geochemists tell us that the uranium is transported as a uranyl carbonate complex. But a mineralogist can tell you what it really looks like. And here's what it looks like. Those needle-like things are the uraninite. Oh, except wait a minute. That's not the normal texture for uranium, like uraninite, like Karen showed, as it's your botryoidal or it's cubic, okay? So what we're really looking at is pseudomorphs, all right? I looked at this for months and I couldn't figure out what it was. I mean, what are some possibilities? Maybe hematite, spectrohematite, maybe molybdenite, maybe graphite. Nah. I got some assistance from an Australian geologist. He said, here's what you're looking at. These pseudomorphs, they're not vesicular, they're actually planar. There's the planar crystals over here. What you're looking at is at boiling temperatures. This is the deposition of calcite in an open space. Now, if you take calcite out of that geochemist complex, what happens? You got to drop the uranium. That's what we're looking at here. So those, now it's flooded with later galena here. And notice there's also some chalcopyrite. Wherever I saw high-grade uranium or higher grade uranium, there was frequent that there was chalcopyrite with it. Now, we're going to look at the same vein, this 1003 vein. And here it is. Oh, looks like normal uraninite in the gray here. It's botryoidal. Hey, but the things that are strange about this, it's got bubbles in it. It's got cracks that are pretty straight. All right. And here is a fracture which goes over and meets one of those bubbles, and it then is filled by chalcopyrite. There's a little bit of coffinite down in here. Again, we're looking at a polysection, and it's a little bit darker mineral. So now, John Haley was the chief mine geologist. He says, yeah, we mined out the 9th level, except for one thing. I have a surveyed down the hole intercept of high-grade uranium, uraninite, just a little bit below the 9th level. So he talks into the mining engineers and he says, let's drive a drift over to the west, about 100 feet and down 10. Now remember, Anaconda's offer price was $8 million. Here's that vein. John was an easygoing Boston guy, veteran of the Korean War. And so they named the vein after him and called it the Titan. When I walked into that stope, it looked like I was in a Western Pennsylvania coal mine. Right as this room. Black as heck. And that was 1 million pounds. Now from Karen's graph, if we get into the 70s, the price goes up for uraninite into the 40s. This vein alone was worth $40 million. Nice. How's the ore handled? Well, coming out of the mine is 4 one-ton cars. These devices are scintillometers, which are going to read dam count or uranium content, and it's on a scale. Well, this green building here is an ore sorter, and I'll explain to you what that is. Here, let's look at a schematic. Ore comes out of the mine, goes to the jaw crusher, 6-inch jaw crusher. Now, think back of what could be in there. It could be ore, and it could be the wall rocks, those gneisses and schist. Okay, if the schist and the gneiss go through, the first hit on the jaw crusher, it's going to break it into a couple of pieces, and probably along the schistosity or gneissic texture. It's just kind of stay big. But if the Schwarzwälder rocks go into that jaw crusher and get shatters, anything under 1 inch goes through a classifying screen, drops, and goes directly to ore pile. Why? Because just by that crushing, that product coming through is minus 1 inch, is 25% upgraded from the head that went in. Nice. Well, there's a minus 6-inch plus 1 fraction, and there's a minus 6-inch plus 2 fraction. That material, for example, here is washed off. It goes to a feeder, and there's going to be troughs coming out. And it's going to gently drop the ore particles on this belt, which is translucent. And it's going to move those particles over top of a high intensity lamp so that they can be photographed. That is, what's their big footprint? Make a shadow. It's going to be black. That data is going to be taken into the analyzer, and then moving past, it's going to go to the highly shielded gamma counter. So it measures the radioactivity of each particle. Now let's take a look and see what it is. So here's the 3-channel ore sorter. Particles are dropping on. Bright lights below. The camera's above out of sight, and it's about to enter the shielded gamma counter. Here's the end. Now, this red belt here is going to freely drop the particle here, and it's got the analyzer is 8 inches to decide whether it's ore or whether it's waste. Waste will drop off, as these particles show here, and if you can see faintly, here's a divider. An air blast comes out if it's ore. That is by 8 100 psi lines here. And so here's a particle just got hit with the humid air, and there's a particle over here going to drop down, and it's going to be propelled on this side. So there's the ore pile. It's ready to get picked up by a front end loader, dumped into the truck, and taken up to about 4 miles down Ralston Creek, waiting there to be hauled by a contractor down I-25 to the mill in Canyon City. Well, here's the White family, which really owned the property. And if you've driven in the area, you see now White Ranch Park. And they had 4 children and the royalty of $70 million. They didn't want to be cattlemen anymore. So, well, Mrs. White comes by the office at the mine in 1979. And she's greeted by some of the management. And one of the persons was Rich Stigler, and he's the treasurer of the company. He says, hello, Mrs. White. He said, now it's a hot August day. He said, back in April, I sent a check to you, but it hasn't come to clear through the bank. Oh, she says, honey, when I go home, it's sitting on the top of my dresser. I'll take it to the bank. That check was about $98,000. Now, the White family, they just big donation to Jefferson County for open space. And I think it was almost 3,000 acres. But the other thing that they did, they donated to this cause, the Warriors on a Cataract. These are our veterans. And many of you have PTSD. And this is directed by Fred Solheim here with assistance from Louis Kleinhaus. And they take our veterans down, and it's really helping their constitution. So here's the mine, almost today. Waste and subore materials are sent up here. Oh, I did forget one thing. When the mine got below about 1,500 feet down, there was a new ore body show up. And that ore body was actually the East Rogers Breccia Reef. Wait, the West Rogers, thank you, Tom. The West Rogers Breccia Reef. It was low grade, but it was big. I agree. Fault mined. And so I don't know what the frequency was, but maybe once a week after blasting and loading in sequential charges, give a call to this campus, which houses the USGS, and say, expect some seismic disruption. Okay. So that didn't go through the ore sorter because it was lower grade. You just take the bulk rock and get rid of it.
What was the cutoff grade in those days? You were there in the 80s, right?
I had it on that diagram. I think it was 0.01, 0.015. Okay, so this is approximately what it looks like. This is when Jim Kappa and I went up to photograph. The mine buildings are taken down now, but here's all this material up here. And now it's green. It's in vegetated. This is about maybe 5 years ago. However, if the introduction was, it's more than a supernova. It's a super fun now because of uranium in the waters. Well, a company called Colorado Legacy Land got the contract. In fact, they actually bought the property. It sounds pretty dangerous, but with liability wise. Well, they bought the property, and as I said in my abstract, they found that 2 plants that could absorb the uranium out of the water to meet EPA standards. So that was good. Well, here are my.
Jim mentioned that water was carrying uranium before the mining ever started.
Well, I have numbers for that. Yeah, but it wasn't that great, but compared to what it is now, because you can believe this. When the mine was shut down by the state, I think I asked, maybe I don't know if I asked you, Tom, but I said, what's going to happen to all that diesel equipment down there? Are going to get crank cases? I said, nah, leave them go. But the state said, just let it go. Okay, all right. Well, the Potter also put in 2 culverts that are kind of upstream from the mine to carry summer flow, so it wouldn't let water filter down. In fact, where I showed you that picture of the big enough for you to walk into, there was a test made of dumping fluorescent dyes in Ralston Creek and checking for that down underground on the 11th level. That dye would show up in 24 hours. So the Colorado Legacy Land this past summer found that these two plants were very good in absorbing the uranium. In fact, it would meet standards. Unfortunately, that company has gone bankrupt. So I don't know if anything's going to happen. I'm sure somebody will take over and put those plants. Now, in my last days after working 4.5 years at the mine and other projects for Carter Corporation, I just wanted to reminisce. I said it was a great place to learn, to study this deposit. So I'm looking at back at the deposit because I'm on the other side of Ralston Creek, looking back at the mine. Okay, I turn around, ready to go back, and I see a pint jar. Hey, it's got a really rusty lid on it. Get it open. Look at that. It's a piece of paper in there. It's a Fred Schwartzwelder claim notice. So I gave it to management. Now, so I go to take a higher salary from the people across the fence. It happens to be Union Pacific subsidiary, Rocky Mountain Energy. They say one of the first things we're going to do is see if there's another Schwartzwelder. So what they do is we're going to fly geophysics airborne, and you can see these lines on here, very closely spaced, low altitude, and this happens to be the the magnetic map. Okay, background is about 55,000 gammas, but the anomaly is 4,000 higher, and it happens to sit right on top the Schwartzwelder ore deposit. Piece of core. Okay. Thank you. Any questions?
I had a comment, you had that picture of the valley. Imagine that before the Schwartzwelder was there, that was a braided stream valley. And that creek was moved over. And that there's a lot of deposition coming, then there were a lot of core holes drilled into the mine. That uranium's coming out today, that's why they're having trouble with everything in the valley.
Oh, okay. In fact,
It was braided, that's why they put that tube through on the other side.
all right, it's good you mentioned that up. When I was on a drill hole down in just the bottom of the valley of the mine, and they were just finishing up the third level cap, the drill hole was about maybe 1,000 feet down, and it's about maybe 1,000 feet from the mine. They were pumping concrete down to the bottom of the shaft, and the drillers said to me, "Watch this. You could have their drill steel was vibrating sequentially with them pumping into concrete."
I wanted to make a comment about all the nice samples that people brought in the back. Don't ignore them. And one of them I didn't mention was from the Rossing deposit. It's a nice sample. And the Rossing was 0.01% uranium. And it absolutely was not necessarily economic, but it's in Niger and the labor was dirt cheap. And so the French paid the labor and they mined the deposit. So that made it economic. But I just wanted to say there's lots of good, I've never seen so many uranium samples as back there. And then Jim's got ones up front here for the Schwartzwelder.
Yeah, Jim?
Yeah, a few years ago, I asked you about the right line up near Idlewild,
Yeah, right.
and you said that you looked at that, drilled it.
Right.
You were looking at a number of different shear zones along the front range. Did you ever find anything that looked like it might have potential?
No, it wasn't big enough to meet Carter, but that right mine's vein actually crops out right at the highway. Okay, and you can pick it up with a Geiger gun. Well, this is the rock that I said that I had assayed, and well, you can see the yellow chalcopyrite.
What were the two plants that were effective in uranium?
Okay, in the abstract is the author's paper, and it was given at Vancouver in, I think, April this past year. Okay, and it's mentioned in there. I don't remember. Yeah, Tom?
I had one other comment on, on closing the mine, there was always thought of whether there was a down thrown block of the Schwartz rock on the west side of the West Rogers that might be down about 4,000 feet, a couple thousand feet below the bottom of the mine. The bottom of the mine and then was at 2,300, which was the spiral decline below the bottom of the 1,900 level. And I don't know, nobody's ever really explored that because nobody's come with the money to drill it.
Well, they called me back to look at it, and I looked at the ore, and it was about 900 feet horizontally. Gone through, the schist, so it's not worth anything. Okay, if you do that, you got to drive at it or a drift over about 900 feet long. How are you going to get it vented,
But
you get some kind of run along vent line, so they decided, we looked at fluid inclusions, okay, and some of this. As it turned out, the fluid inclusions suggested boiler. Okay, on some, in fact, the Marbury vein, remember that?
Right.
And that was running 10%, and that was still at the bottom of the mine. I'm not saying how big it was, but still, that was the assay, 10%.
Was on 19.
Yeah,
Karen, you mentioned somewhere where they were drilling 6-foot diameter cores.
MacArthur River,
Where? MacArthur River?
that's how they're mining it.
Okay, so I wanted to share that out in Temple Butte, Utah, they had something that was called calyx mining. And they weren't, what, 6 feet, but they were,
There was 3 feet. That's how they operated out of this 3-foot bore. You go down in line and bring the ore up, I'd get claustrophobic.
yes,
So Karen, you mentioned earlier that you could see molybdenum in the uranium roll fronts. Are there any other rare earth elements or critical strategic elements that could be found within a uranium roll front? And would they be leachable?
I haven't analyzed the samples, roll front samples. My guess is the answer is no, that the sandstone roll fronts don't have you don't have the pure uraninite. I mean, you don't have the big flow grade. So I think it takes a higher grade uraninite sample to incorporate, and also the mechanism of deposition makes a big difference too. But I don't know, I haven't analyzed them like we did. I mean, we pulled a lot of samples apart from some of the big mines and did the laser ablate ICP spectroscopy on it and microprobe, but we didn't do it on any of the sandstone deposits. But again, you've got to get some nice pure uraninite to be able to do that. So, yeah, it has, moly, of course, and moly often goes with the roll fronts, and you get vanadium because hence the uranium mineral belt where it gets its name. And there's a lot of 3D transition metals associated with a lot of the uranium, especially the breccia pipes have nickel, cobalt, zinc, lead.
that coarse sample with uraninite with the bubbles in it, that sample ran 3.8% molybdenum. Okay, and anywhere from 5 to 60 times crustal of exceeding 5 to 60 times the average crustal abundance of rare earth elements in it. So like Karen said, the rare earths are captured or
In the uraninite. And the Schwarzwälder has accelerated contents of rare earth elements too.
Steve?
Yeah, can you say something about wall rock alteration? Was there wall rock? I mean, it's such a classical.
Oh, yeah,
vein system.
Here's a.
Was there a change vertically over this great distance that you mined vertically?
I don't think so. I mean, I didn't recognize it. I'm sorry, but here, okay, here's a little uraninite vein going through here, and then here's the hematite, and then look at the bleaching takes place peripheral to that on the sides.
So is the hematite related to cogenetic with the uraninite?
Yeah.
That's odd.
Well, yeah, I mean, well, it's, I'm impressed by how a little bit of hydrothermal introduction causes such a wide spacing alteration. Yeah.
Question from online. Bruce Geller wanted to know what form the silver was in the Schwarzwälder.
I don't know, but the mine called down to the mill. He said, we've got a lot of silver in this, so what are you doing with it? Oh, they said it's on the dump.
So silver is not uncommon. It's probably associated with uranium, whereas gold not usually. I mean, you get some in some of the Australian deposits and of course, South Africa. By the way, the Liebigite, didn't mention that's highly fluorescent and that's hexavalent uranium. You notice it looks a lot like the uranium glass down here. And by the way, here's a trick question for you guys. How radioactive is uranium glass? And the answer is it's about as radioactive as yellow cake. If you have fresh yellow cake, how radioactive is yellow cake? If you take a cinelama to it. Is your question for you guys.
Yeah.
See if you pass the oral comprehensive exam here. The answer, does that have someone have an answer to it? The answer is, Larry?
Well, I just remember going to a mine in Africa and handling the yellow cape with maybe gloves, and they said, don't worry about it, it's very low radioactivity.
Yeah, it's because, your scintillometer is measuring bismuth 214. And if you really remember that decay series I put up there, but bismuth 214 is a daughter product like radon and radium of uranium, but the half-life of the uranium is enormous. And so if you've just processed and geochemically processed the uranium into yellow cake, none of the daughter products are there, they're gone. And it's the same thing with the uranium glass down here. It's geochemically refined, they've just stuck uranium in it. And Jim wants to fluoresce his rock.
Okay, well, this is trying to sweater because. Okay, here's
Whoa.
this is stuff on the screen.
That's your hexavalent uranium, and it's not radioactive because of the fact that you've geochemically isolated the daughter products are gone, and you just have the uranium with enormously long half-life.
Just a comment, there was a mineral collector in Boulder County who had from Shinkolobwe a fist-sized sample that was 100% UO2. So it's pitch point. What's really interesting, if you take that to sell it, you will get let's say it was 5 pounds, you will get 5.5 pounds of U3O8. Because if you calculate it, there's actually 5.5 pounds of U3O8 in 5 pounds of UO2.
Oh, right. By the way, I just heard that you can't sell mineral specimens on uranium specimens, on eBay anymore. They are outlawing it. So some of the mineral collectors have code words now, and they're putting the mineral specimens on with code words.
Yeah, regarding Karen's comment on the Dalton Sea geothermal field. When I was with the Sarco in the 60s and 70s. They were in the first generation part of that geothermal field constructed casing because of the mineral precipitate. And they brought some of the Sarco and assayed, analyzed. And it was very high grade silver ore, several percent. So the Sarco bought all of their case cleanings there for several years.
Oh, yeah, probably true.
Zinc too. Yeah.
So there's the answer to your question about what do they call about what they did with it. It looks like they're fighting over it. Sort of like the golf course is trying to take the Palo Verde nuclear power plant's wastewater away now.
They have a bunch of that stuff.
Several questions.
It's really-
What's the age of the deposit? What's the general ore deposit model that would fit into? Because maybe with the precipitation mechanism. And then how is all that related and involved with the magnetic field? That's good stuff.
Was the pipe scale.
And the timing on the deposit. It's been 68 million, okay. 68.3, okay. Well, the nearest thermal source is the Ralston Dike. That's been measured at about 65.8 million years. So say, oh, okay. The dike wasn't the source. However, the dike is right on strike at Rogers Fault. The Rogers Fault, what does that meet? Golden. Okay, hey, that's, you got two faults working right here, okay? And a PhD thesis, dissertation done on the mine, where it was believed that the uranium and the metals came out of the wall rock, the country rock, made that uranium. However, if we look at the age of the deposit, how do you get metals to traverse through amphibole grade gneisses? In fractures, opening, not in the wall rock. That bothers me. Your last question?
The magnetic anomaly.
Yeah, well, I'm sorry, it's the rocks in that, remember the marine sequence that mica schist. Then essentially like Hawaii, basalt's laid over top of that. And we're seeing quartzites in the Schwarzwälder host rocks, so maybe we're coming down to the surface of land at the time. That's all I can say.
So there's not a magnetite body there or metamatic.
There's Algoma style iron.
There's our information.
Yeah.
That's what the.
Yeah, in fact, one of those northwesterly structures is called the Iron Dike.
Jim?
By the way, I hope we've gotten people who are under 40 in this room, there aren't too many of you, enthused about uranium and that you've, are really interested in it because you never know where it might come in handy. Because remember, I was a volcanologist originally and I got turned into a uranium geologist. So.
Jim, has anybody looked at the sulfur isotopes in the sulfides in the Schwarzwälder? I could imagine looking at that golden fall that they could have come out of basin fluids from some of those reduced rocks, sulfur and basin fluoride rich basin fluids.
No, all we did is mass spectrometry. That's how we got this, our other. I don't know. I've got a few samples, and Sam Rawberger had a few samples. But he got trouble when he was at the Berthoud Hall because the state was coming down the elevator and their counters went off in the elevator. He said, where's that coming from? He found his office. And so I said, I didn't say there was 20 billion pounds delivered from this ore deposit, okay? Subtract a few 100 pounds for Sam's office samples.
Yes.